Tonight, we are going to board a ship that has never been built. This is a ship at the absolute different page of what the laws of physics will allow. And we are going to ask one question. How far could it carry a human being before the universe itself says no? Here is the part almost nobody expects. The answer has nothing to do with engines. Because right now, as you are watching this, roughly 94% of everything astronomers can see in the deep sky is already out of reach. Permanently. That is true for this ship. For any ship we could ever build. And for any ship our descendants could build 1,000,000 years from now. The stars are not waiting for us. Every single second. Thousands of them slip across an invisible line. And once they cross it, no traveler leaving Earth will ever touch them again. The night sky you looked at as a child is partly a map of real destinations, and partly a museum of places that are already gone. But the 6% that remains is bigger than anything the human mind was built to hold. And what a single person could do inside that 6% will sound impossible by the time we get there. By the end of tonight, you will know how far one human body could actually go, how far a whole civilization could spread, and why some journeys are forbidden by the universe itself. If you love falling asleep to questions this size, take a second to like this video or subscribe. It helps this channel reach more curious minds like yours. Now, let us begin. Picture the launch complex on the morning of departure. There is no crowd, no countdown broadcast around the world. Because this launch does not belong to any particular year. The ship standing on the pad is a thought experiment made of metal, the best vessel that physics will permit. And we are going to treat it seriously for the rest of the night. Inside the crew module, a traveler is strapping into a seat. We are not going to give this person a name or a face. They are simply the one who goes. They could be you. Before the hatch closes, 2 clocks are placed side by side on a steel table. They are identical, built by the same hands, accurate to a billionth of a second. A technician synchronizes them, and for one moment, they agree perfectly. Then one clock is carried aboard the ship, and the other is bolted to a wall back on Earth, in a quiet room where it will keep counting no matter what happens. Right now, those 2 clocks tell the same time. They will never agree again. Hold on to that image, because those 2 clocks are going to carry us through everything that follows. They will explain things tonight that equations never could. The hatch seals, the ship rises, and through a small window, the traveler watches the Atlantic tilt away beneath them. Then the curve of the planet, then the whole Earth shrinking into a blue circle, then a blue point, then a pale grain of light lost among other lights. Every astronaut who has ever seen this describes the same feeling, a kind of protective ache, the sudden understanding that everything they have ever loved fits inside a single, fragile pixel. Our traveler sees it for a few minutes. Then the window fills with stars, and Earth is simply one of them. Now, before the engines push toward anything ambitious, we should be honest about the question we are asking, because it is really 4 questions wearing one disguise. How far can a living body survive? That is one answer. How far can our machines and engines actually carry us? That is a different answer. How far can a traveler go as measured by their own beating heart, their own birthdays, their own aging face in the mirror? That answer, as you will see, is so strange that it sounds like fantasy, and yet it is among the most rigorously tested physics we have. And finally, how far can humanity itself reach? Over thousands of generations. If we stop thinking about one ship and start thinking about a species, 4 questions. 4 very different distances. The universe grades each one separately. The traveler settles in for the long burn ahead. On the wall of the crew module, their clock ticks quietly, still in perfect step with its twin on Earth. At least for now. But before we imagine the farthest place a human might ever stand, we have to be honest about how little distance we have actually crossed. Let us leave the traveler coasting for a moment and take an honest measurement of our species. Because there is a strange gap at the heart of human spaceflight, a gap between what we can see and where we have stood, and most people have never really felt the size of it. Start with the largest circle, the reach of our eyes and instruments. Telescopes like Hubble and James Webb have photographed galaxies whose light left them more than 13 billion years ago. When the universe was a newborn, in terms of pure vision, humanity has already surveyed almost the entire observable cosmos. We have watched stars being born in clouds of gas, thousands of light years away. We have measured the atmospheres of planets orbiting other suns. Our sight, in a very real sense, has already touched the edge of time. Now draw a smaller circle, the reach of our voice. Since the first powerful radio broadcasts in the early 20th century, our signals have been spreading outward at the speed of light in an expanding bubble. That bubble is now a little over 100 light years across. It sounds enormous. Against the Milky Way, a disk 100,000 light years wide containing several hundred billion stars. Our century of radio chatter is a bubble so small that on a map of the galaxy it would be less than a single pixel. If the Milky Way were the size of the United States, everything humanity has ever broadcast would fit inside a small town. Draw a smaller circle still, the reach of our machines. The farthest object our hands have ever built is Voyager 1. Launched in 1977, now more than 15 billion miles from home and still going. Some of you watched our journey with that spacecraft. Following it 1 trillion years into the future, 15 billion miles sounds heroic. And it is. It is also less than 1/500th of the distance to the nearest star, our boldest machine. After nearly 50 years of flying, has barely stepped off the porch. And now the smallest circle of all, the reach of the living human body. The farthest any beating heart has ever traveled from Earth is the far side of the moon, about 240,000 miles away. In December of 1968, and on 8 missions after that, a handful of astronauts made that crossing. Light covers the same distance in under 1.5 seconds. That is the true frontier of our species, measured not in light years, and not even in light minutes, but in light seconds. Fewer than 30 people have ever gone that far. No one has been back in over 50 years. Feel the shape of those 4 circles for a moment. Our eyes reach billions of light years. Our voice reaches about 100. Our machines have crossed 23 light hours. Our bodies have crossed 1.5 light seconds. Each circle is unimaginably smaller than the one before it. And the innermost circle, the only one that involves actual living humans, is so small that on any honest map of the galaxy, it does not exist at all. Here is one way to hold it. Shrink the observable universe down to the size of planet Earth. On that scale, the entire Milky Way galaxy becomes a disk about the size of a small city. The distance to the nearest star becomes a few feet, and the full extent of human travel, every mission ever flown, every astronaut who ever lived, fits within a speck smaller than a single grain of sand resting somewhere on a sidewalk in that city. We are a civilization that can see the whole planet, so to speak, while having personally walked no farther than the width of 1 grain on 1 street. Why the gap? Why can our sight cross the universe while our bodies remain pinned within arm's reach of home? Part of the answer is distance itself. And we will feel the full violence of those numbers soon. But the deeper answer is stranger. And it is the first wall our traveler is about to hit. A spacecraft is a very forgiving passenger. Voyager needs no air, no water, no warmth, no gravity, no food, no sleep, no compagnie, and no reason to keep going. A human being needs every single one of those things. Every day, without exception, for years or decades on end. The hardest problem in interstellar travel is not the rocket. It is the soft, warm, breathing cargo the rocket has to keep alive. Back aboard the ship, the traveler is 3 months into the journey, and something quiet has started happening to them. Nothing dramatic, no alarms. Their body has simply noticed that Earth is gone, and it has begun, cell by cell, to fall apart. This is the strangest truth in all of spaceflight. The human body is the most refined machine we know of, tuned by 4 billion years of evolution, tested against ice ages and plagues and famines, capable of healing its own wounds and rebuilding its own parts. And every bit of that engineering was tuned for exactly one environment. One gravity, one magnetic field, one atmosphere, one rhythm of day and night. Take the body out of that environment, and it does not adapt to the new one. It starts searching for the old one. And when it cannot find it, systems begin to shut down. Start with the skeleton. Bone feels permanent, but it is living tissue, constantly tearing itself down and rebuilding itself in response to the load it carries. In weightlessness, that load vanishes, and the body draws a ruthless conclusion. It decides the skeleton is no longer needed. Astronauts on the space station lose roughly 1 to 1.5% of their bone density every single month. Their skeletons dissolve into their bloodstream, and their bodies flush the calcium away as waste. On a 6-month mission that is survivable, on a journey of years, the traveler is slowly being unbuilt from the inside. Their bones thinning towards something like advanced osteoporosis, until a stumble against a bulkhead could snap a hip that was healthy at launch. The muscles follow the same logic, including the one muscle that matters most. The heart is a pump designed to fight gravity, lifting blood out of the legs all day. Every day, take gravity away and the heart, like any idle worker, gets weaker and smaller. Astronauts return from long missions with hearts that have measurably shrunk and rounded. Eyes change shape too, because the fluid that gravity used to pull downward now drifts upward and presses against the optic nerve. Some astronauts come home with their vision permanently altered. 3 months out, our traveler already notices the print on their screens going slightly soft at the edges. Then, in the 2nd year, comes the problem. No shield fully stops. Radiation. Earth protects us twice. First with a magnetic field that deflects charged particles. Then, with an atmosphere as protective as a slab of metal many feet thick. Out here, the traveler has neither. Galactic cosmic rays. Atomic nuclei, accelerated by exploding stars, arrive from every direction at nearly the speed of light. And they pass through aluminum hulls, through water tanks, through flesh and bone and the double helix of DNA, leaving microscopic scars along the way. The Apollo astronauts learned about this personally. When they closed their eyes to sleep on the way to the moon, they saw flashes of light inside their own eyelids, streaks and sparks in total darkness. Those flashes were cosmic rays passing directly through their eyeballs and striking their retinas. Every flash was a bullet of starlight going through a human head. They saw one every few minutes. over months. That invisible rain raises cancer risk, damages the brain, weakens the immune system, and there is no practical thickness of shielding that stops all of it. Pack on more armor, and the cosmic rays shatter against it, spraying secondary particles that can be worse than what came in. The traveler's ship carries its water and fuel wrapped around the crew quarters as a buffer. The best trick we know, and even so, a counter on the wall quietly tallies the dose, year after year. But ask anyone who has actually flown long missions what the hardest part was. And they rarely say bones or radiation. They say the mind. There is a moment on this ship that no human being has ever experienced. It happens in the second year. Since the day our species opened its eyes on the African savanna, every human who ever lived has had the earth with them. Every sailor on every empty ocean still had it under their feet. Every astronaut on the moon could look up and see it hanging in the black. Blue and alive and clearly home. Our traveler floats to the window one evening, ship time, and searches for it, and cannot find it. Earth has dimmed below the threshold of the naked eye. It is somewhere in that field of stars behind them, indistinguishable from 1,000 faint points. The window still shows everything humanity has ever known. It just no longer shows it as anything. Psychologists who study isolation in Antarctic crews and submarine crews see the same pattern again and again. The mind frays without novelty, without weather, without strangers, without the option of leaving. Small irritations grow into feuds. Sleep collapses. And every crew in history could at least tell themselves that home was months away. On this ship, the truth is harsher. If something breaks in the traveler's body or in the traveler's mind, there is no rescue, no resupply, no turning around. A blocked appendix, an infected tooth, a failed air filter, a psychological break in a crewmate. Any one of these, out here, is a countdown. And beyond all of it waits the question medicine has never answered, because it has never dared to run the experiment. Children. No mammal has ever been conceived, carried, and born in deep space. We do not know if a human embryo can develop normally without gravity to guide it. We do not know what cosmic radiation does to a child in the womb. We do not know what happens to an infant whose bones and heart and inner ear have never once felt the pull of a planet. Any journey longer than one lifetime runs directly through those unknowns. And right now, the honest answer to every one of them is that nobody on Earth knows. So, this is the first wall. And notice that we hit it before we ever discussed an engine. How long can a body built for Earth survive after Earth is no longer behind it? With current knowledge, the answer is measured in a few years. And every one of those years costs bone, muscle, vision, blood, and peace of mind. But suppose we solve it. Suppose the ship spins to create gravity. The shielding holds. The crew stays whole. And children can be born among the stars. Solve every problem of flesh. And you run straight into a wall that has no sympathy at all. Because this one is written in mathematics. Every rocket that has ever flown obeys one equation, and that equation has a cruel sense of humor. Here is the joke it plays. You want to go faster, so you carry fuel, but fuel has weight. And now your ship is heavier, so you need more fuel to push the fuel you brought. And that new fuel has weight too. So you need still more fuel to push that. Follow this loop, and the demand does not grow gently. It grows explosively, feeding on itself, until the rocket is almost nothing but its own propellant. Look at any rocket on any launch pad in history, and you are looking at a skyscraper of fuel with a closet of cargo balanced on top. The Saturn V that carried men to the moon stood over 360 feet tall and weighed about 6.5 million pounds at liftoff. And more than 90% of that weight was propellant. The 3 astronauts and their capsule were a rounding error riding on a bomb, and the equation is not finished with you, because it holds a second joke in reserve. Arriving somewhere is not the same as passing it. If you ever want to stop at your destination, to orbit it, to land on it, to live there, you have to kill every bit of speed you built up, which costs just as dearly as building it did. And the fuel you plan to burn at the far end must be hauled, unburned, across the entire journey, which means the vicious loop starts all over again. Bigger than before. Speed is a loan, and the universe always collects. Now let us take this unforgiving arithmetic and climb the ladder of destinations, one rung at a time, and watch what happens to the price. The moon sits about 240,000 miles away. 3 days of travel with chemical rockets. Humanity has paid this price 9 times with crews aboard. Call this the first rung. Mars, at a reasonable alignment, sits about 140 times farther than the moon. The trip takes 6 to 9 months one way, and the fuel demands are steep enough that half a century after Apollo, no space agency on Earth has yet managed to send a single person. That is the second rung. And notice that we are still standing on our own doorstep. The outer solar system is the third rung. Jupiter, Saturn, the ice worlds beyond. Robotic probes need years to get there, and a crude round trip with chemical propulsion would consume more time than most careers and more fuel than any nation has ever been willing to launch. Then comes the fourth rung, and this is where the ladder simply breaks. Proxima Centauri, the nearest star to our Sun, sits about 4.25 light-years away, roughly 25 trillion miles. Take the fastest outbound machines we have ever built, the Voyagers, moving at about 38,000 miles per hour. At that speed, the crossing to Proxima Centauri takes more than 70,000 years. 70,000 years ago, humans had not yet painted the caves of Europe. Whole ice ages have come and gone in less time than that one trip. A boat is not a slower version of a starship. It is a different category of machine entirely. And everything we have ever launched, every rocket, in every museum and on every pad today, belongs to the boat category. So the engineers of our travelers' civilization went looking for something better. And this is the arsenal they found. Watch what each weapon costs. The first upgrade is nuclear power. Split atoms instead of burning chemicals and you can roughly double your efficiency. Maybe better? Fission engines could shrink the trip to Mars from months toward weeks and turn the solar system into a place humans actually work. This technology is close. We tested engines like it in the 1960s and are designing them again now. But run the numbers on a fission starship and your heart sinks. Against 25 trillion miles. Doubling a hopeless speed still leaves you hopeless. The solar system becomes a backyard. The stars do not move an inch. The second upgrade is fusion, the fire of the sun itself. In the 1970s, a team of scientists and engineers ran a famous study called Project Daedalus and designed, on paper, a fusion ship that could reach roughly 12% of the speed of light. At that speed, a nearby star comes within reach in about 50 to 100 years. For the first time on this ladder, a human institution could conceivably span the gap, a single long lifetime, or one handover between parents and children. Now the price. The Daedalus design weighed over 50,000 tons, mostly exotic fusion fuel that would have to be mined from the atmospheres of the outer planets. And the ship could not stop when it arrived. It would spend decades crossing the void and then scream through the destination system in a matter of hours. Cameras snapping, and vanish back into the dark. Remember the second joke of the rocket equation. Braking doubles the price, and Daedalus could not afford to pay it. The third upgrade is antimatter, the most concentrated fuel physics allows. When matter meets antimatter, both vanish entirely into energy. A conversion hundreds of times more potent than fusion. A few dozen pounds of it could, in principle, drive a ship to a healthy fraction of light speed. Here is the price tag. All the particle accelerators on Earth, running for decades, have produced a combined total of a few billionths of 1 gram. Producing it consumes vastly more energy than the antimatter ever gives back. And storing it is a nightmare with no full solution. Because the instant it touches the walls of any normal container, it detonates. Antimatter is real, and it is the most expensive substance humanity has ever created. And a starship would need it by the ton. Which brings us to the cleverest idea of all. The one that finally outsmarts the rocket equation instead of fighting it. Leave the fuel at home. Build an enormous bank of lasers on Earth or in orbit. Aim them at a ship fitted with a vast mirror-thin sail, and push it with light itself. The ship carries no propellant at all, so the vicious loop never starts. This is the idea behind Breakthrough Starshot, a real program studied by real physicists today. And their math says a laser array could drive a tiny probe to 20% of the speed of light, reaching Proxima Centauri in just over 20 years. For a machine, the door to the stars is genuinely, mathematically open. Now look closer at that word tiny. The probe in question weighs about 1 gram. A paper clip. To push it, the laser array must briefly focus about 100 gigawatts, comparable to the output of 100 nuclear power plants firing at once onto a sail the size of a room. That is the price for 1 gram. Our traveler, their ship, their water, their food, their shielding, their landing gear, everything a living human needs, weighs hundreds of millions of times more. Scale the laser up by hundreds of millions, and you are no longer describing a machine. You are describing the entire energy budget of a planetary civilization, aimed at one departing sail for years without blinking. And when that ship arrives at the far end, there is no laser array waiting there to slow it down. Do you see the pattern now? Every rung of this ladder sells you a new speed and hands you a new impossibility. Fission buys the solar system and nothing beyond it. Fusion buys a flyby it can never break from. Antimatter buys performance in a fuel that barely exists. Lasers buy starflight for a paperclip. There is no perfect engine anywhere on the shelf. Each way of going farther trades an old limit for a new one. And the trade is never generous. So the traveler's civilization faced this ledger and drew the only sane conclusion, with any engine we can honestly foresee. A journey to even the nearest stars takes longer than a human life. And if the ship cannot be made fast enough, then perhaps the thing that has to change is the passenger. Before we follow that dark and fascinating road, hold one image in your mind. The 2 clocks, the one on the ship and the one bolted to the wall back on Earth. They are still ticking in step, agreeing with each other the way they have since the technicians synchronized them on that steel table. But somewhere far ahead on this journey, those 2 clocks are going to start disagreeing. Not by seconds, by centuries. And strange as it sounds, that disagreement is not a malfunction and not a problem to be solved. It may be the closest thing to a gift the universe has ever offered us. We will get there. First, the passengers. There is a room on the traveler's ship that we have not visited yet. It sits behind the crew quarters, kept dim and quiet. And inside it are the plans that engineers drew up for the day. Humanity finally admitted the truth. If the voyage takes centuries, and the passenger only lasts decades, then one of them has to change. And since the length of the voyage is set by physics, the thing that changes will have to be us. The oldest and most haunting of those plans is called a generation ship. The idea is brutally simple. Build a vessel so large that it is no longer a vehicle but a world. A sealed cylinder miles long, spinning to create gravity. With farms and water cycles and weather, home to thousands of people. Launch it toward a distant star, knowing the trip will take 500 years. The crew that departs will grow old and die on board. So will their children. So will their grandchildren. Somewhere around the 20th generation, descendants who have never seen Earth, whose great-great-grandparents never saw Earth, will look out the forward windows and watch a new sun grow bright. Sit with what that actually means for the people in the middle. Think about a woman born in year 240 of the voyage. She opens her eyes inside a metal cylinder. She learns to walk on a floor that curves up into the sky. She grows up, falls in love, works a job keeping the air clean or the crops alive, raises children, grows old, and dies, all within the same few miles of corridor. She never chose this journey. Her ancestors signed her up for it centuries before she was born. Earth, to her, is a set of old videos, a planet as mythical as Atlantis. The destination is a promise she will never see kept. Her entire existence, from first breath to last, happens inside a hallway between two worlds, and she will touch neither one. The engineering problems of such a ship are enormous. Keeping a closed ecosystem stable for centuries. Keeping machines running without a hardware store within trillions of miles. Keeping the population genetically healthy from a starting crew of thousands. But the deepest problems are human. A ship like this needs its society to hold together longer than most nations on Earth have existed. Consider what 500 years does to any culture. 500 years ago, no country that exists today had its current form of government. Languages have shifted so much that English speakers can barely read the English of that era. Now ask a sealed village in a metal tube to keep believing in the mission. Generation after generation. While nobody aboard has ever seen the world that launched them, or the world they are promised, historians who study this problem talk openly about mutiny, about religion changing, about some future generation simply deciding they do not care about a star chosen by ancestors 7 centuries dead. The machinery might survive the voyage. Whether the mission survives the people is another question entirely. So, engineers looked for a way to skip the middle generations altogether. And that is the second plan in the quiet room. Sleep through it. Cool the passengers down. Slow their bodies to a crawl. And wake them at the destination with only a few years of aging spent. Science fiction loves this idea, and nature teases us with it. Because bears and ground squirrels genuinely do shut their bodies down for months at a time. But here is the honest state of the art. Medicine has never put a human being into true hibernation. Not once. Not for a single day. Hospitals can chill a patient for a few hours during certain surgeries. And that is our species' entire resume. Human cells are not built for the long pause. Freeze them, and ice crystals shred them from the inside. Merely chill them, and they starve and suffocate in slow motion. Perhaps some future biology cracks this. But it is worth being clear that hibernation, the most casually accepted piece of furniture in every space movie, is a technology that does not exist at all. The third plan is stranger and colder. If full-grown humans are too heavy, too hungry, and too fragile to ship. Then do not ship them. Ship the seeds. A vessel the size of a small truck could carry hundreds of thousands of frozen human embryos, each one weighing almost nothing. Each one a complete future person on pause. Frozen embryos are proven technology today. Machines could carry them across the centuries, and robotic systems at the destination could, in principle, grow the first generation. Feed them, teach them, raise them. And right there, the plan runs into a wall that has nothing to do with engineering. Those first children would open their eyes on a world with no parents in it. Machines would feed them. Machines would speak to them. Machines would comfort them when they cried at night. Every human being who has ever lived learned what love and trust and language are from another human being. What exactly grows up in a nursery run by software? 4 light years from the nearest human touch. The children would carry our genes, whether they would carry anything else of us. Our warmth, our humor, our way of being people. Nobody can say. We would have successfully shipped human biology across the stars, while possibly leaving humanity itself behind on the launch pad. There is a fourth plan whispered about in that room, the most radical of all. Skip the body completely. Scan a mind. Copy it into a machine. And beam or carry the copy across the void at a fraction of the cost of shipping flesh. If it works, distance almost stops mattering. But let us file this idea exactly where it belongs. Nobody knows whether a mind can be copied. Nobody knows what consciousness even is. Whether it is software that can move between machines or something inseparable from the warm biological tissue it grew in. And even if a perfect copy could be made, there is a question that should keep you up tonight. If a copy of your mind wakes up around another star, convinced it is you, while you remain here and eventually die on Earth, did you travel anywhere at all? Or did you just create a stranger who remembers your childhood? Look at what every one of these plans has in common. Each begins as an engineering solution and ends as the same question wearing a different mask. The generation ship arrives carrying people who never knew Earth. The embryo ship arrives carrying people raised by machines. The uploaded ship arrives carrying something that may or may not be a person. In every case, something reaches the destination. And in every case, you have to ask, if no one aboard lives to complete the journey, did humans make it there at all? Or did we just send a very elaborate message in our own handwriting? Hold that question. Do not answer it yet, because it comes back at the end of tonight wearing its final form. And notice the assumption buried underneath this entire chapter. The assumption every plan in the quiet room accepted without a fight. All of them agree that the journey must take longer than a life, that the distance is fixed, the speed is capped, and time is simply the toll. Every scheme we just walked through is a way of paying that toll. With generations, with sleep, with frozen seeds, with copies. But what if the toll itself is negotiable? What if the universe, hidden inside its strictest law, left a loophole about time? To find it, we have to do something that sounds reckless. We have to take our traveler's ship, aim it at deep space, and push the throttle toward the one speed the universe has posted as an absolute limit. Because the loophole is not written anywhere else. It is written into the wall itself. The traveler's ship is about to attempt something no human vehicle has ever attempted. A run toward the speed of light. And the universe is about to fight back in ways that almost nobody expects. This chapter is that fight. First, understand the wall itself. Light moves at 670 million miles per hour. In the time it took you to hear that sentence, a beam of light could have circled the Earth more than 50 times. Nothing made of matter has ever reached that speed. And according to every experiment ever run, nothing made of matter ever will. This is the most tested law in all of physics. Particle accelerators like the ones at CERN have been trying to push protons through that wall for decades, feeding them absurd amounts of energy. And the protons get to 99.999% of light speed and simply refuse to go faster. The energy keeps pouring in. The speedometer barely moves. Why? Because the universe changes the rules. As you speed up, at everyday speeds, energy buys velocity at a fair price. Push twice as hard. Go faster in proportion. But as you approach light speed, the exchange rate turns against you. Gently at first, then viciously. Getting from 90% to 99% costs far more than everything you spent getting to 90. Getting from 99 to 99.9 costs far more again. Each additional decimal place costs more than the entire journey before it. Climbing toward infinity. And infinity is not a big number. It is the universe's way of saying never. The wall does not need a guard. It simply raises the price without limit and lets your bank account do the refusing. So the traveler's ship will never touch the wall. But it can get close. And close, it turns out, is where space itself turns hostile. The first enemy is one you would never suspect. Dust. Interstellar space is the emptiest place there is. But it is not perfectly empty. Drifting between the stars are sparse grains of rock and ice, most of them smaller than a period on a printed page. At normal speeds, they are nothing. Voyager has been plowing through them for 50 years, without a scratch worth mentioning. But the energy of a collision grows with the square of your speed. And at relativistic velocity, that little multiplication becomes a monster. Run the numbers, and they stop sounding like science and start sounding like a threat. A single grain of dust weighing 1 gram, about as much as a raisin, striking a ship at 90% of the speed of light, delivers the energy of roughly 20 kilotons of TNT. That is the Hiroshima bomb, packed into a raisin. At these speeds, there is no such thing as debris anymore. Every mote of dust on the flight path is a warhead with no fuse, waiting in the dark. And the galaxy has scattered trillions of them exactly where you need to fly. The second enemy is even stranger, because the second enemy is light itself. As the ship accelerates, something eerie happens to the view ahead. Starlight coming toward the bow gets compressed, squeezed to shorter and shorter wavelengths. Shifted up the spectrum, gentle red stars turn white, then blue. Keep accelerating, and the compression keeps going. Past blue, past violet, into ultraviolet and X-rays. The soft glow of the galaxy, the same starlight poets have written about for thousands of years, hardens in front of the ship into a beam of radiation. Even the faint microwave whisper left over from the Big Bang, the coldest and gentlest signal in nature, gets squeezed into something that can burn. Near light speed, the universe does not need to throw anything at you. Its own scenery becomes the weapon. The faster you flee toward the stars, the more fiercely the stars themselves push back. The third enemy is time, in its cruelest form. Reaction time. Suppose the ship's sensors are magnificent and can spot a pebble in the flight path at a range of 1 million miles. Sounds like plenty of warning. Now do the math. At 99% of light speed, the ship covers 1 million miles in about 5.5 seconds. And there is a nastier catch underneath. The radar pulse you send ahead travels at light speed, barely faster than the ship chasing it. By the time the echo returns to say, "Danger ahead," you have nearly caught up to the danger yourself. Warning and impact arrive almost hand in hand. At relativistic speed, the ship is effectively flying blind into a minefield, outrunning its own headlights. And behind all three enemies stands the accountant, the same one from the rocket equation, now presenting a bill with more zeros than any civilization has ever seen. The kinetic energy of a single crewed ship at 99% of light speed rivals the total energy output of all humanity sustained for centuries. And the old joke still applies. If you ever intend to stop at your destination, double it. So, look at where we stand. Because this is the lowest moment of the night. The body fails within years. The engines top out hopelessly short. The passengers can only cross the gulf by dying along the way, sleeping through their own lives, or dissolving into copies. And now, the final highway itself. The approach to light speed turns out to be lined with bombs, floodlit with radiation, and priced beyond the wealth of worlds. Every road we have walked tonight ends at a wall. And this last wall has a sign on it that reads, "Never." But stay with me, because we are now standing exactly where the story turns. Everything I just described, the dust, the deadly light, the impossible bill, is the wall as seen from outside, by observers watching the ship from a safe distance, by mission control back on Earth. Physics, however, has been keeping a secret about what happens on board. A secret it only reveals to those who get close to the wall. The speed of light is not merely a barrier that blocks motion. It is a hinge on which space and time themselves swing. And for anyone riding near it, the universe quietly begins rewriting the two most basic facts of any journey. How far? And how long? Back on that steel table on launch day, a technician synchronized two clocks, and we made you a promise about them. The ship is now moving fast enough to collect on that promise. Before we say a single word about starships, I need to tell you about an experiment that sounds like a prank. In October of 1971, two physicists named Joseph Hafele and Richard Keating walked onto ordinary commercial airliners carrying 4 atomic clocks. They bought seats for the clocks. The clocks flew around the world, first eastward, then westward. Drinks cart rolling past. Passengers reading newspapers beside the most precise timekeeping devices on Earth. Meanwhile, identical atomic clocks stayed behind at the United States Naval Observatory in Washington. When the flying clocks landed and were placed next to the stay-at-home clocks, they disagreed. The difference was tiny, a few hundred billionths of a second. But it was real. It was measured. And it matched Einstein's predictions almost exactly. The clocks that flew had experienced a different amount of time than the clocks that stayed. Please understand what this means, because it is the hinge of the entire night. This is not a metaphor. This is not a trick of perception or a mechanical error. Time itself, the actual amount of existence that passed, was different for the travelers than for the ones who stayed home. Motion changes how much time you experience. At airliner speeds, the change is a whisper, buried in the 9th decimal place. Our traveler's ship is about to turn that whisper into a scream. And if the airplane experiment sounds too exotic to matter to you, reach into your pocket. Your phone finds your location using GPS satellites. And those satellites are moving fast enough, in a weak enough gravity, that their onboard clocks genuinely run at a different rate than clocks on the ground, drifting out of step by about 38 millionths of a second every day. That sounds like nothing, but GPS works by timing signals that travel at the speed of light. And at the speed of light, 38 millionths of a second is about 7 miles. If engineers did not correct for Einstein every single day, Your map app would place you in the wrong neighborhood by tonight and in the wrong city by the weekend. Relativity is not a theory that lives in textbooks. It lives in your pocket. And it is switched on right now. So, the two clocks from launch day, one bolted to a wall on Earth, one mounted in the Traveler's crew module, synchronized to the billionth of a second on a steel table. Here is what happens to them as the ship accelerates. At 10% of light speed, the disagreement begins. Though it is still polite. The ship clock runs about 0.5% slow compared to Earth's. A year aboard. And the Traveler is a couple of days younger than their records back home say they should be. Pushed to 87% of the speed of light. And politeness ends. The ship clock now runs at half the rate of the Earth clock. For every year the Traveler lives, breathes, eats, and sleeps. 2 full years pour through the clock, bolted to that wall back home. Birthdays on Earth come twice as often as birthdays on board. Pushed to 99.5%. And the ratio hits 10 to 1. 1 year aboard. 1 decade at home. Pushed to 99.995%. And it becomes 100 to 1. The Traveler spends a single year reading, exercising, and watching the strange sky. And back on Earth, an entire century turns over. Everyone who waved at the launch is gone. Now here is the part that separates the people who have heard of relativity from the people who actually understand it. So let me slow down and get this exactly right. The Traveler feels nothing. Nothing aboard the ship changes. Their heart beats at its normal rhythm. Their coffee cools at the normal rate. Their thoughts move at their normal pace. Seconds feel like seconds. Boring afternoons feel long. Good books feel short. If they check their own pulse against their own clock, everything matches perfectly. Because their body and their clock are slowing together. In the same boat. In the same river of time. There is no sensation of slowness. No molasses feeling. No sign whatsoever that anything unusual is happening. The ship's clock is not broken. The Earth clock is not broken. Both clocks are doing flawless work. What has changed is something underneath both of them. The relationship between motion, space, and time itself. Speed does not damage your clock. Speed changes how much time there is for you. I know how this sounds. It sounds like philosophy. Or word games. It is neither. It is engineering fact. Verified in airliners in 1971. Verified in your phone today. Verified every hour in particle accelerators. Where unstable particles that should die in microseconds live dozens of times longer simply because they are moving fast. Their tiny internal hourglasses genuinely slowed by speed exactly as Einstein calculated. The universe has been running this experiment for us millions of times. And the answer always comes back the same. So now, walk through the door that this fact opens. Because it changes the meaning of every distance on every star map we own. Take a destination 1,000 light years away. Common sense says a ship needs at least 1,000 years to get there. So, no passenger survives the trip. End of story. And common sense is correct. For Earth, watched from home, the voyage takes just over 1,000 years, no matter what. But the passenger is not standing on Earth. The passenger is in the fast river, where time flows differently. And if the ship runs deep into the 99s, the passenger's share of those 1,000 years might be 20 years, or 10, or 5. Both of the following statements are true at the same time, and neither one cancels the other. On Earth's calendar, the journey takes 1,000 years. On the traveler's calendar, it does not. A destination can sit 1,000 light years away on the map, and still be reachable within one human lifetime. By the only calendar that matters to the person making the trip, their own aging body. There it is, the loophole. The universe caps your speed and then quietly hands you a discount on time. And the discount grows without limit the closer you push toward the wall. Distance, it turns out, was never the whole truth about a journey. The rocket equation is merciless. The light barrier is absolute, and yet hiding inside that very barrier is the most generous clause in all of physics. Before you get too comfortable, though, read the fine print, because there are 3 lines of it, and none of them are kind. First, the energy bill from the last chapter has not shrunk by a single dollar. Reaching the deep 99s still costs more than worlds. The loophole is real, and the price of using it remains absurd. Second, nothing here breaks the wall. Light still wins every race. The discount applies to the traveler's experience of the trip, never to the trip as Earth measures it. And third, the heaviest line of all. While the traveler saves time, Earth keeps spending it at full price. Those 1,000 years at home really do pass. The traveler cannot phone home and find the world they left, because that world is aging away at the normal rate. Generation after generation, while they cross the void in their few private years. The discount is real, and someone absolutely pays. The traveler may cross the distance without growing old, but everything they left behind will. Now we get to run the experiment that this entire night has been building toward. We take the traveler's ship, the best vessel physics allows, and we make one simple, almost gentle demand of it. Accelerate at 1 g. That is all. 1 g is the acceleration you are feeling right now. Sitting wherever you are. The ordinary pull of Earth. A ship that accelerates at 1 g pushes its floor up against the crew's feet with exactly the force of home, and that turns out to be its own quiet miracle. Because the cruelest problems of Chapter 3 simply dissolve. Bones stop dissolving. Hearts stay strong. The traveler walks the corridors, drops a pen and watches it fall, cooks dinner, does push-ups, lives under what feels precisely like Earth gravity, manufactured out of nothing but constant forward thrust. No spinning rings, no medical countdown. Just keep the engine burning, gently, forever. That is the whole trick. Hold 1 g and never let go. Watch what it buys. After about 1 year of shipboard time, this gentle, everyday push has carried the ship to the edge of light speed itself. Read that again, because it is the number nobody believes at first. Falling forward at ordinary Earth gravity for 1 year delivers you to the doorstep of the universal speed limit. From that point on, the ship cannot gain much more speed. What it gains instead is time discount, the gamma factor. The gap between the 2 clocks starts to soar, and the star map starts to shrink. Here is the itinerary, and I will give it to you honestly, with the fine print attached to every line. These figures assume the ship accelerates at 1 g to the halfway point, flips around, and brakes at 1 g the rest of the way, so that it actually arrives and stops rather than screaming past. And yes, the fuel for such a journey is beyond anything we can currently build. This is a test of what physics permits, never a forecast of what engineers will deliver. With that said, physics permits the following. Proxima Centauri, the nearest star, 4¼ light years away. Shipboard time, about 3½ years. A student could leave Earth at 22 and walk on a world of another sun before turning 26. The center of the Milky Way, 26,000 light-years away. The great glowing hub our entire solar system orbits. Shipboard time, about 20 years. One career. A person could depart at 30 and arrive at 50. Having crossed a distance that light itself needs 260 centuries to cover. And the edge-to-edge crossing, the whole galaxy. 100,000 light-years of stars and dust and darkness. If the ship does not stop, if it simply holds its 1G burn and threads the entire disk in a straight line, the crossing takes about 12 years of shipboard time. Add braking to stop at the far rim, and it is roughly 24. Either way, the sentence that results should not be possible. And yet it is simply what the equations say. A human being could be born on Earth and die of old age on the far side of the galaxy, with decades to spare. And why stop at the rim? Andromeda, the next great galaxy over, sits 2.5 million light-years away. A distance so obscene, we usually only mention it to frighten people. At 1G with braking, the shipboard clock charges about 28 to 30 years for the trip. A crew could leave Earth in their 20s and step out under the light of an entirely different galaxy in their 50s. 28 years of grey hairs to cross an ocean that light needs 2.5 million years to swim. While those years pass, the view from the front window becomes something no artist has painted correctly. As the ship digs deeper into the 99s, the geometry of light itself starts folding. Stars that should be beside the ship, even stars that should be behind it, have their light bent forward by the ship's own velocity, and the entire sky begins to migrate toward the bow. The heavens gather themselves into a tightening ring of light dead ahead, blue, white, and fierce at its center, while behind the ship, the blackness spreads, emptier than any night ever seen from Earth. The traveler is flying down a tunnel whose walls are every star in the sky, pulled forward and stretched into streaks by their own passage. Meals still happen. Laundry still happens. Somebody has a birthday, and there is cake. 12 candles worth of them scattered across a crossing of the entire Milky Way. That is the journey on the ship's clock. Now comes the part of the chapter that hurts, because we have to read the other clock. The moment the ship arrives at Proxima Centauri, 3.5 years old, to its crew. The clock on that wall back on Earth reads just under 6 years. Not so bad. Friends have aged. Kids are taller. The world is recognizable. Right home. And the reply, crawling back at light speed, still finds people who remember your face. But look at the Earth clock when the ship reaches the galactic center. The crew has lived 20 years. Earth has lived 26,000. Let that number find its footing. 26,000 years ago, there were still mammoths. No city existed anywhere on the planet. No wheel. No writing. No farm. Every single word of every language spoken on launch day has had time to be born, evolve beyond recognition. And the country that built the ship, whatever country that was, has not merely fallen, it has been forgotten, rediscovered by archaeologists, argued about, and forgotten again. The crew's 20-year voyage did not carry them to another place in their world. It carried them completely out of their world, into a future so distant that their entire civilization is a stratum in the ground. And Andromeda is worse, in a way. Numbers barely communicate. The crew steps off after 28 years. Earth's clock has turned over 5 million years, roughly 1,000 times the age of all recorded history. And here is the detail that ends every argument. 5 million years is longer than our species has existed. Whatever is living on Earth when that ship arrives, whatever is reading the ancient records of a vessel that departed for Andromeda in the deep past, It is not Homo sapiens. The travelers themselves, stepping down onto some new world in their 50s, are at that moment the last members of a species that no longer exists anywhere else. The final humans, alive and well. 2.5 million light years from a home that outgrew them 50,000 centuries ago. This is the moment to look at the two clocks side by side. One last time before the night takes its darkest turn. On the ship, the clock has counted 20 years, and it has counted them perfectly. On Earth, the clock has counted 26,000, and it has counted them perfectly too. Neither clock lied, but somewhere out in the dark between them, those two clocks stopped measuring the same journey. One still measures a voyage. The other now measures the distance between two histories. So this is the bargain, written out in full. Physics will let one human being cross the galaxy, and even reach the galaxies beyond, inside a single ordinary lifetime. The toll is never paid in years. The toll is your era, your language, your species, every person who could ever have understood where you came from. The ticket to the far side of the sky is one way, not because the ship cannot turn around, but because the world that launched you will not exist to come back to. And after everything we have seen tonight, you might think that is the final shape of the answer. Time bends, distance yields, and the only real cost is homesickness on a cosmic scale. Give a civilization enough patience and enough power, and surely everything we can see is eventually within reach. It is not, because beyond our galaxy, something is happening to the map itself. The distances out there are not sitting still waiting for us. They are growing, and they are growing in a way that no engine, no loophole, and no amount of time can ever beat. Let us follow the traveler off the edge of the map, because that is literally what happens next. Every journey we have described so far, no matter how enormous, took place inside the Milky Way. Inside a city of stars, where the next streetlight is never more than a few years of shipboard time away. Now the ship crosses the rim of the galactic disk. The last thin scattering of stars falls behind, and the traveler enters the space between galaxies. And almost immediately, something becomes clear that no star map ever quite communicates. Everything we have called empty tonight was crowded by comparison. Interstellar space, the gulf between stars, holds about one lonely particle in every cubic inch. And we spent half this night marveling at that emptiness. Intergalactic space is thousands of times emptier still. Out here, there are no stars for the window, no nebulas, no landmarks of any kind, just the ship's own lights reflecting off its hull. And beyond them, a blackness with a texture no human eye has ever tested. If interstellar space is a desert, this is the open ocean at midnight with no floor beneath it. For a crew, that emptiness is a double-edged blade. There is nothing to hit, which is mercy at relativistic speed. And there is also nothing to use. No gas to scoop for fuel. No comets to mine for water. No sunlight to catch. Whatever the ship carries through this ocean is all it will ever have. Break something out here, and the nearest replacement atom of civilization is millions of years of light away in every direction. The nearest port on the far shore is Andromeda. And Andromeda deserves a proper introduction, because you can see it yourself. On a dark autumn night in the northern hemisphere, away from city lights, there is a faint grey smudge in the constellation of the same name, about the size of the full moon. If your eyes were sharp enough to catch its full extent, that smudge is 1 trillion stars. It is the most distant thing the naked human eye can see. And when its light entered your eye, It had been traveling for 2.5 million years. It left Andromeda before our species existed, crossed the void while glaciers advanced and retreated and our ancestors slowly learned fire and language, and finished its journey on your retina. On a random Tuesday, unnoticed. Here is the piece of luck the traveler is counting on. Andromeda is coming to us. Some of you know this from our night with Voyager. The Milky Way and Andromeda are falling toward each other at about 250,000 miles per hour, bound by gravity, destined to merge billions of years from now into a single giant galaxy. For an intergalactic traveler, that approach means the finish line moves toward the runner during the race. Every year of the crossing, the far shore is closer than the charts at launch predicted. It is a small kindness against a 2.5 million light-year gulf, but it points at something enormous, something that becomes the hinge of the rest of tonight. The destinations are moving. The map is not a map of places. It is a map of moments, and the places have kept moving since the light left them. With Andromeda, the motion is friendly. Now widen the view, and the friendliness ends. Astronomers in the early 20th century, led by Edwin Hubble, pointed their telescopes beyond Andromeda and started measuring the motion of other galaxies. Hundreds of them, then thousands, and a pattern emerged that nobody wanted, because it sounded less like astronomy and more like abandonment. Outside our immediate gravitational neighborhood, essentially every galaxy in the sky is moving away from us. All of them, in every direction, and the pattern had a second layer that was stranger than the first. The farther away a galaxy is, the faster it recedes. Double the distance, double the speed of retreat. Galaxies 10 times farther flee 10 times faster. It is as if the universe had quietly reorganized itself around one rule. Whatever is far from you is getting farther, and the far things are getting farther, fastest. We will save the full explanation for where it belongs a little later tonight, because it deserves the stage to itself, and because what it implies is the single strangest fact in this entire story. For now, the traveler only needs the picture. So, here is the picture. Every galaxy is an island. The traveler's ship is a boat that has left the shore of one island, aiming for another. But the water between the islands is not ordinary water. The ocean itself is stretching, quietly, everywhere, all the time, the way dough stretches while bread rises. Islands drift apart without ever sailing anywhere, carried by the widening sea itself. Nearby islands, like Andromeda, sit close enough that the local currents of gravity overpower the stretching, which is why Andromeda can still fall toward us. But the far islands are another matter. Out there, the stretching of the ocean wins, and it wins bigger with every mile of remove. The traveler is not chasing an island that sits waiting on a fixed sea. Beyond our neighborhood, every voyage is a race between a boat with a top speed and an ocean with none. And that sentence has teeth. Hold it up next to everything we learned about the wall. The speed of light is the absolute limit for the boat. Nothing made of matter or information can move through space faster. But watch the wording, because the whole night turns on it. The limit applies to things moving through space. The stretching of the ocean is not a thing moving through space. It is space itself changing size. And the speed limit has nothing to say about it. Add up enough stretching over a long enough distance, and two islands can effectively recede from each other faster than any light beam could ever connect them, without either island moving at all, without any law being broken. The universe never runs. It simply grows. And growth, unlike speed, has no posted limit. Feel what that means for the question we came here to ask. Every barrier so far, the body, the fuel, the dust, even the light barrier itself, was a wall standing between us and a destination that at least stayed put. This is different. For the first time tonight, the destination itself is in motion away from us, carried by the deep structure of reality. And the farther the island, the faster the water between us grows. So, the honest question is no longer how fast the boat can go. The question is, which islands can still be caught at all? And which ones the ocean has already carried beyond every possible voyage? That accounting is coming. And I will tell you now, the numbers are not kind. But before we open that ledger, the question itself has to grow one more size. Because we have spent the whole night asking how far one traveler in one boat can go, and a single traveler was never going to be the right unit of measurement for a species. Come back to the near side of the ocean for a while, back inside the Milky Way, because something has been quietly wrong with our question all night. And this is the chapter where we fix it. Every wall we have hit was a wall for one ship, one hull, one crew, one lifetime, one fuel tank, launched from one planet toward one destination. Frame the problem that way, and the galaxy is a fortress. But humanity has never actually expanded that way. Not once in our entire history. No single Polynesian canoe set out to cross the whole Pacific. What crossed the Pacific was a process. A canoe reached the next island, and people settled it, planted it, raised children on it, built new canoes from its trees. And a generation or three later, some of those children pushed onto the island after that. No individual sailor ever traveled more than a fraction of the whole span. The wave of settlement crossed an ocean that no sailor could. Now run that same play on the galaxy, and watch every impossible number from earlier tonight fall over. Un by un. Humanity, or whatever humanity becomes, establishes itself around a nearby star. Call it Proxima. Call it Tau Ceti. The name does not matter. The first crossing is brutal. Everything tonight has told us how brutal, perhaps generations long. But the settlers are not tourists. They arrive and they build. They mine the asteroids of the new system, farm energy from the new sun, raise children who consider that sun the normal color a sun should be. And after a few centuries of growth, that system does what Earth once did. It builds ships and launches its own settlers at the next stars. Over 2 systems become 4. 4 become 8, then 16, then 100. The frontier is no longer a ship. The frontier is a wave. And a wave does not age, does not run out of fuel, does not lose heart. Every generation of the wave starts fresh, fully fueled, at the edge of wherever the last generation stopped. Here is what stuns everyone who works through the arithmetic. Give the wave modest tools. No warp drives. No exotic physics. Just ships at 10% of light speed. The kind of performance fusion designs like Daedalus were already sketching on paper in the 1970s. Let each new settlement pause for centuries before launching onward. No rush at all, even under those patient, conservative assumptions. The wave sweeps across the entire Milky Way. All 100,000 light-years of it. Every star, every world, in somewhere between 1 million and 10 million years. I know that number sounds like a long time. Now put it on the universe's calendar. The Milky Way is more than 13 billion years old. 10 million years is less than 1/10 of that age. If the galaxy's whole history were compressed into a single year, The complete settlement of every one of its several hundred billion star systems would take about 6 hours. One afternoon, on the galaxy's calendar, a civilization takes over the entire Milky Way in less than a heartbeat, using engines we have already imagined, at speeds we already believe are buildable. Sit with how strange that is. The same galaxy that is an impassable fortress to one ship is a weekend project to a patient species. And if you are wondering why, if it is that easy, the galaxy does not already seem to belong to somebody. Congratulations. You have just independently discovered one of the deepest riddles in science. The question the physicist Enrico Fermi asked at lunch one day in 1950, and which nobody has answered since. Where is everybody? The math says waves like this should have swept the galaxy many times over by now. The sky says otherwise. The silence between those two sentences is one of the great open questions of our age, and it deserves its own night. Tonight, we stay with our own wave, because there is a catch in the wave strategy, and by now you can probably smell it coming. Nothing about it is free. This time, the toll is deeper than an era. Ask what actually arrives at the far side of the galaxy, 10 million years after the wave leaves Earth. The settlers of each new system adapt to that system. Different gravity thickens or lightens their bones. Different suns retune their eyes. Centuries of separation turn dialects into languages. Languages into mysteries. 10,000 years is enough for evolution to visibly reshape a population. And the wave has 1,000 times that long to work with. Add the tools a starfaring people will certainly possess. The ability to edit their own genes, to harden their bodies against radiation and time, perhaps to move their minds into sturdier vessels than flesh, and follow the wave far enough. And the beings stepping off the ships onto the last worlds of the Milky Way, 10 million years from now, share almost nothing with us. Our bones are not their bones. Our senses are not their senses. Earth, to them, is a rumor of a rumor. A name in databases so old they need archaeologists of their own. Some of the frontier may not be biological at all. The cheapest wave to launch is a wave of machines. Self-replicating probes that land on dead moons. Mine them, copy themselves, and launch onward, needing no air, no food, no patience. A galaxy can be explored entirely by such messengers, carrying our knowledge, our image, maybe our recorded voices, to shores no living thing ever reaches. So, here is the question of the chapter. And notice it is our old question from the generation ships, grown to its final size. If the beings who complete the journey have changed their bodies, their genes, their minds, their languages, and possibly their definition of being alive at all, is that still us arriving? Or is it something we became when the wave reaches the far rim of the galaxy? Has humanity traveled 100,000 light years? Or has humanity stayed home and sent its descendants? The way a tree does not travel when the forest spreads. I am not going to answer that. And I want to be honest about why. There is no answer. There is only a choice about what you count as us. Count only unmodified Homo sapiens. And our species probably never leaves the solar neighborhood in any numbers. Count everything downstream of us. Every child of every child, however changed. Every mind that traces its lineage back to this one blue world. And then the whole Milky Way is genuinely, plausibly ours. Reachable, not in some fantasy future, but through processes as ordinary as emigration and birth. And with that, we can finally assemble the great ladder of tonight's answers. 1 unaided human body. A few light seconds. 1 heroic crew in the best ship physics allows. Another galaxy within a lifetime. At the cost of their entire era. 1 patient civilization. An entire galaxy of several 100 billion stars. At the cost of becoming something new along the way. Each time we widened the definition of we. The reach exploded. A body. A lifetime. A species. Each unit larger. Each horizon farther. So, take the largest unit of all. An immortal civilization. Patient beyond meaning. Armed with every technology physics permits. Spreading wave upon wave for billions of years. Surely for that traveler, everything is reachable. Surely, given enough time, such a civilization inherits the entire universe. Every galaxy, every star we have ever photographed. That feels like it should be the answer. It is not. And the reason it is not is the strangest thing you will hear tonight. At the very beginning of tonight, I made you a promise. I told you that roughly 94% of everything astronomers can see is already permanently out of reach. And I told you the reason had nothing to do with engines. It is time to pay that promise in full. This is the chapter where the whole night has been heading. And I will warn you now. It changes the way the sky looks. Start with the 2 phrases everyone treats as the same thing. The observable universe and the reachable universe. They sound like twins. They are not even cousins. The observable universe is everything whose light has had time to arrive here. A sphere about 93 billion light years across, holding somewhere in the neighborhood of 2 trillion galaxies. It is the universe of photographs. The universe of every deep field image that ever made your jaw drop. The reachable universe is a different thing entirely. It is the set of places a ship or a signal leaving Earth today could ever arrive. Given unlimited time and the best speed physics allows. And here is the fact that rearranges everything. The reachable universe is vastly smaller than the observable one. And it is shrinking while you listen to this sentence. Seeing a galaxy is proof of only one thing. That light left it long ago. Sometimes seeing a place is only proof that it existed. Once, to understand why, come back to the stretching ocean from earlier tonight. Because now we can look at it directly. In 1998, 2 rival teams of astronomers were measuring distant exploding stars, trying to clock how much the expansion of the universe was slowing down under gravity's pull. Everyone knew it had to be slowing. The only question was by how much. Both teams got the same answer. And the answer broke the question. The expansion is speeding up. Something woven into empty space itself. Something we have labeled dark energy, because we genuinely do not know what it is pressing the universe outward. Harder and harder. And it does not weaken with time. The stretching ocean is not coasting. It is accelerating. Now, recall the loophole in the loophole. The speed of light limits everything that moves through space. It says nothing about space itself. Between us and a sufficiently distant galaxy, so much new space is being created every second that the total gap grows faster than light could ever close it. The galaxy is not speeding anywhere. We are not speeding anywhere. The road between us is getting longer, faster than anything is allowed to drive. Picture the ant and the rubber band, because this is the picture that makes it click. An ant walks along a rubber band toward a crumb at the far end, and the band is being stretched while the ant walks. If the band stretches slowly, the ant wins eventually. But if the band stretches fast enough, something merciless happens. Every inch the ant gains. The stretching adds two more in front of it. The ant never stops walking, never slows down, never breaks a single rule of ant physics. And the crumb gets farther away every hour. Forever. That ant is every photon we will ever send, every ship we will ever launch. Beyond a certain distance, the crumb cannot be caught, and the fault lies with the band, never with the ant. That certain distance has a name, the cosmic event horizon. In the standard model of cosmology, it currently sits around 16 to 17 billion light-years from Earth. Inside that radius, a light beam leaving tonight will, someday, arrive. Outside it, no light beam, no radio signal, no ship, no matter how perfect, launched from here tonight will ever arrive. Not in a trillion years. Not in any number of years you can write down. The word for those places is simply never. And now do the accounting that this horizon forces on us. Because this is the number I owed you from the first 2 minutes of tonight. Take the 2 trillion galaxies of the observable universe. Ask how many still sit inside the reachable zone, close enough that a ship leaving now, traveling arbitrarily close to light speed, could someday arrive. The answer is roughly 6%. 6%. The other 94% of everything in our photographs. Hundreds of billions of galaxies, each holding hundreds of billions of stars. Each star, a possible sun over possible worlds. All of it is already on the wrong side of the line. Already. This is the part people resist. So, let me say it as plainly as physics allows. Those galaxies are not going to be lost someday, in some remote future. If we dawdle, the losing already happened. The band between us and them is already stretching faster than light can walk. A ship launched tonight toward the Hubble Deep Field, carrying the best of everything our descendants will ever invent. Chases targets that were carried out of range before you were born. For 94% of the pictured universe, the photographs are all there will ever be, and the line is still moving. In the wrong direction. The acceleration never rests, which means galaxies near the boundary are being carried across it continuously. Galaxy by galaxy. The reachable universe is emptying out. Break that down into stars, and the arithmetic turns into something almost physical. On average, every single second that passes, thousands upon thousands of stars cross the horizon, each one carrying its planets, its moons, its possibilities. From the column marked someday into the column marked never. It happened while I said that sentence. It will happen again before I finish this one. You are living inside a slow-motion evacuation, and the exits are sealing in strict order of distance. Farthest first. Working inward. Here is the detail that gets me every time. The one that turns all this physics into a feeling. We will keep seeing them. Light that left those galaxies millions and billions of years ago is still en route. Still arriving faithfully. And it will keep arriving for eons. The galaxy itself may already be unreachable. Permanently. Absolutely. And yet its portrait keeps refreshing in our telescopes like a letter stream from a sender who moved away long ago. Nothing in the sky announces the difference. The reachable and the unreachable shine side by side, identical to every instrument we own. The night sky is, in part, a museum. Some of its lights are windows. Some of its lights are memorials. And there is no label telling you which is which. The universe does not need to build a wall in front of us. It only needs to carry the destination away faster than we can close the distance. Everything else tonight had a workaround, and it is worth taking one breath to notice that The body was the first wall, and we found spin gravity, shielding, the 1G burn. The rocket equation was the second, and we found fusion, sails, waves of settlement. The speed of light was the third, and hiding inside it, we found the greatest loophole in physics. Time itself, bending in the traveler's favor. Every wall so far had a door. Somewhere. For someone clever enough and patient enough. This wall is the first one with no door in it. Because it is the first wall that is not standing between us and the destination. This wall is the destination. Receding. You cannot out-engineer geometry. You cannot outweight acceleration that never tires. Patience was our superpower in the last chapter. An immortal civilization spreading on a 10 million year schedule. Against dark energy. Patience is worse than useless. Because dark energy is also patient. And its patience compounds. Somewhere far out on the ocean between galaxies, our traveler receives all of this the way crews receive everything. As data on a screen. The Great Survey, the Horizon Math, the 6%, and in the archive of their ship there is a live feed, maintained across the whole voyage out of something between discipline and love, showing one particular clock bolted to one particular wall, still ticking in a quiet room. On a planet the traveler has not seen with their own eyes since the window went dark all those chapters ago. The clock has kept flawless time through everything. Through the fall of the country that built it. Through the drift of continents' worth of history. Through the slow turnover of everything the traveler would recognize as home, the clock still ticks. It has simply outlived the world it was set in. It counts the hours of a planet where the traveler's language is no longer spoken, where the launch is no longer remembered, where the steel table and the technician and the morning of the synchronization survive nowhere except aboard the ship that left. The clock still ticks. The time it was built to keep is gone. That is what the horizon does. One relationship at a time. On the grandest scale there is. It does not destroy anything. Every one of those 9,400 billion galaxies goes right on shining, right on birthing stars, right on, existing in full. It only cuts the threads between things, quietly, permanently, until the universe becomes a collection of separate rooms whose doors have vanished. Each room still bright, each room forever alone. And I know exactly what you are thinking, because every person who ever learned this thought it in the same breath. Wormholes, warp drives, bending space, punching through, cheating. If the ocean cannot be outrun, maybe it can be tunneled under. That is precisely the right question to ask. And it deserves a real answer instead of a wave of the hand. So let us ask it properly. Every physicist who gives a public lecture about the cosmic horizon gets the same hand in the audience afterward. And the question behind that hand is always some version of the same hope. What about the tricks? What about the doors in the walls of the universe that science fiction promised us? Tonight, that question gets a full and honest hearing. And to keep us honest, we are going to sort every idea into one of three boxes. Things physics has proven. Things mathematics allows but nature has never confirmed. And things that are pure speculation, dressed in equations. The boxes matter. Because the whole difference between science and wishful thinking is knowing which box you are standing in. Open the first box, the proven one, and something lovely is sitting inside. We already cheat. Time dilation. The two clocks. The 12-year galaxy crossing. All of Chapter 8. That is a genuine cheat code against distance. As verified as gravity itself. It flies in your GPS satellites every day. It has been measured in airliners. in particle accelerators, in atomic clocks raised one single foot above their twins. The universe truly does allow a human lifetime to span 100,000 light years. Never forget how astonishing that is. The one legal cheat is already miraculous. But everything in this box shares one property. It bends time. Never the map. It makes the journey survivable for the traveler while doing absolutely nothing about the stretching ocean. Against the horizon, the proven box is empty. So, we open the second box, the mathematics box. And here the night gets strange and beautiful. Because Einstein's equations, the same equations that built the wall, contain solutions that look exactly like doors. The first is the wormhole, and its pedigree is impeccable. In 1935, Einstein himself, working with a young physicist named Nathan Rosen, found that his equations permitted a kind of bridge, a shortcut connecting two distant regions of space through a tunnel outside of ordinary space. The mathematics is genuine. General relativity, the most successful theory of space and time ever written, does not forbid such bridges. A wormhole with one mouth near Earth and the other mouth in a galaxy beyond the horizon would beat the ant and rubber band problem completely, because the ant would stop walking along the band and step through it instead. The distance being stretched simply would not matter anymore. Now, the fine print. And in this box, the fine print is everything. The bridges in the raw equations collapse instantly, faster than anything could cross, slamming shut like a mouth. Holding one open requires threading the tunnel with something physicists call exotic matter, material with negative energy, stuff that in a certain sense weighs less than nothing and pushes space apart rather than pulling it together. Quantum physics does permit whispers of negative energy in tiny amounts, in laboratory effects between metal plates. But the quantities a traversable wormhole demands are astronomical, and nothing in nature has ever been observed to supply them at any scale beyond the subatomic. The door is drawn perfectly in the blueprints. No one has ever seen the material the hinges must be made of. The second resident of the mathematics box arrived in 1994, and it came from an unexpected direction. A physicist named Miguel Alcubierre, openly inspired by watching science fiction, sat down to check whether a warp drive could be written in the language of general relativity, expecting to prove it impossible. Instead, he found a solution. His idea is pure elegance. Never move the ship. Move the space. Compress the space ahead of the vessel. Expand the space behind it. And let the ship ride inside a bubble of ordinary calm, like a surfer carried by a wave they are not swimming in. Inside the bubble, the ship never exceeds light speed, never even accelerates. No crushing forces, no time dilation, and yet the bubble itself, being a deformation of space rather than an object in space, can cross the map at any effective speed whatsoever. Remember why the horizon exists at all. Because space itself stretches without a speed limit. The Alcubierre drive is the audacious suggestion that we use the same loophole, that we do deliberately, locally, on purpose. What dark energy does blindly across the cosmos? Fight the ocean with the ocean. The fine print again. The original math demanded exotic negative energy in quantities that beggared belief. Early estimates ran to more than the mass energy of the entire observable universe. Decades of refinement have carved that number down spectacularly, to planetary masses by some accounts. And a few recent papers even explore designs claiming to soften the exotic matter requirement altogether, though those claims remain contested and unproven. The honest summary is this. The warp drive has spent 30 years moving from absurd toward merely unbelievable. And that direction of travel is interesting. But no warp bubble has ever been created. No exotic matter has ever been produced in bulk. And severe theoretical problems remain, including what happens at the bubble's edge and whether causality itself starts to bleed. It is a door drawn in flawless mathematics. Waiting on materials nature may simply not stock. Mathematics can describe a door without proving that nature allows anyone to build it. That sentence is the entire second box. And it deserves a moment of quiet, because both of its failures are the same failure. The wormhole and the warp drive each require negative energy at scale. And the universe, so far, has answered every request for it with silence. The third box holds everything else. And I will be brief with it precisely because it is bottomless. New physics beyond relativity. Shortcuts through higher dimensions. Exploiting some undiscovered structure of space. It is all speculation without a shred of evidence. And it belongs in this box until evidence exists. And yet, the third box should never be sealed or sneered at. For one reason that history keeps teaching. The second box used to be empty too. Flight was impossible physics until it was engineering. The atom was unsplittable until 1938. Our current map of what cannot be done is drawn by a species that discovered the expanding universe about one long human lifetime ago. Humility cuts both ways. It forbids us from promising doors, and it forbids us from promising there are none. So here is where the honest ledger stands. With proven physics, the horizon is absolute, and 94% of the sky is memory. With the mathematics box, there exist blueprints, genuine ones, bearing Einstein's own signature, for doors through everything, waiting on a substance no one has ever found. And if some future century does find it, then everything tonight has told you becomes merely the story of our infancy. The way stories about impossible flight now read to us. But we deal in what is known, and on everything known, the answer is in, and it is time to draw the final map. So, how far could humans ever travel into the universe? We have spent the whole night earning this answer, and now we can finally draw it the way it deserves to be drawn, as a set of circles, spreading outward from where you are sitting right now. You may remember that we opened tonight with circles that shrank, from the reach of our eyes down to the reach of our bodies. And it felt humbling. These circles grow. Watch how far they go before they stop. The first circle is drawn with the technology we hold today, or could hold within a generation. Chemical rockets, early nuclear engines, the machines of the near future. That circle contains the Moon, Mars, the asteroids, and with real ambition, the moons of Jupiter and Saturn, the solar system, our home star and its family of worlds. For creatures who have currently traveled 1.5 light seconds, this circle alone is an empire 1,000 lifetimes could not finish exploring. The second circle belongs to technology that does not exist yet, but breaks no rules. Fusion engines, laser sails, generation ships. The patient machinery of Chapter 5. That circle reaches the nearest stars, Proxima Centauri, Tau Ceti, a few dozen suns within a handful of light years, reachable by crews who trade decades or whole generations for the crossing. Slow, costly, heartbreaking, and permitted. The stars are legal. That is worth saying out loud. Because, for most of human history, we did not know even that much. The third circle is the one that still astonishes me after everything we have seen tonight. Give one crew the finest ship physics allows. a vessel holding 1 g of acceleration without rest. And the circle explodes outward beyond all intuition. The center of the galaxy in 20 years of shipboard time. The far rim of the Milky Way inside a working lifetime. Andromeda itself. An entire other galaxy. In about 28 years, by the clock on the wall of the crew module, one human being, one heartbeat, one aging body, can legally cross intergalactic space before that body grows old. The price never appears on the ship. The price appears at home, where 26,000 years, or 5 million, pour through the other clock, and the world that launched the voyage dissolves into deep time behind it. The fourth circle belongs to no single traveler. It belongs to the wave, the civilization that spreads the way forests spread. Star by star, settlement by settlement, changing as it goes. That circle swallows the entire Milky Way in a few million years. A heartbeat on the galaxy's calendar, and it keeps going. Because gravity has bound our galaxy to Andromeda and to dozens of smaller companion galaxies in a family astronomers call the local group. An island of galaxies about 10 million light-years across. Some of you already know what becomes of it. The Milky Way and Andromeda will merge into a single vast galaxy, the one astronomers have nicknamed Milky Way, and the whole local group will slowly gather itself together over the ages. Here is what matters tonight. That family is bound. Gravity holds it against the stretching ocean, the way a knot holds against a current. Everything inside the local group stays reachable forever, no matter how violently the universe expands beyond it. Trillions of stars, hundreds of billions of worlds, gathered and kept. That is the true inheritance. The largest estate the universe will ever legally sign over to us. And there the circles stop. The fifth circle cannot be drawn, because the fifth circle is the horizon. And the horizon is not a distance, it is a verdict. Beyond the gravitationally bound neighborhoods, the ocean wins. Everywhere. Always. 94% of the photographed universe sits out there, shining in our telescopes, sending light like letters from a sender who has already moved beyond every possible reply. No engine reaches it. No patience outlasts it. Unless the second box someday opens. Unless nature turns out to stock the exotic material those beautiful blueprints demand. The answer past the local group is the plainest word in the language. Never. So the full answer to tonight's question runs like this. Farther than any ancestor ever dreamed. Far enough that one lifetime can span galaxies. Far enough that our descendants could hold trillions of suns. And still not far enough to touch most of what we can see. The universe is generous with distance and absolute about limits. It hands us an island of 10 million light-years and an ocean with no far shore. And it does not negotiate. Now, let me tell you how the story ends. Not the physics. The traveler. The ship is old now. It rides at rest in orbit around a world, circling a quiet orange sun. Far up one of the spiral arms of a galaxy that was never the Milky Way. The traveler is old too. They walk the corridor to the crew module slowly these days. The same corridor they have walked since a morning on a launch pad that no longer exists in any record except theirs. On the wall of the module, the first clock is still running. It has counted the years of one human life. Faithfully, from a synchronization on a steel table to this evening. And every second it counted was real, was lived, was theirs. By that clock, the whole impossible voyage fit inside a single lifetime, exactly as the equations promised. And in the ship's archive, updated by mathematics long after the signals stopped, the second clock is still running too. The one bolted to a wall in a quiet room, on a blue planet, in a country whose name survives nowhere else. That clock never missed a tick. It counted through the end of its builders, through the end of their language, through the slow turning of ages that wore every trace of the launch morning down to nothing. It is counting right now, somewhere in the deep past and the deep distance at once, keeping perfect time for an empty room. The second clock is still ticking. There is simply no one left beside it to watch. The traveler looks at both readouts for a long moment, the way you might look at a photograph of your parents when they were young. And here is the thing I want to leave you with. Because after all the walls and horizons of tonight, it would be easy to hear this story as a story about loss. And I do not think that is what it is. Nothing about the limits made the journey smaller. It was the limits that gave the journey a shape at all. A universe where everything could be reached. Eventually, automatically, would be a universe where no destination meant anything, where arriving was as cheap as waiting. Ours is not that universe. Ours hands every traveler a real choice with a real price. This world or that one. This era or the next. Home or the horizon. Choose. Because you cannot hold both. The traveler chose. The clock on their wall holds the proof. One lifetime, spent entirely on the far side of the sky. Whatever was lost stayed lost. Whatever was reached was truly reached, and could only be reached by someone willing to let go of everything behind them. We can see 2 trillion galaxies. We can touch a few. Maybe the deepest lesson of the whole night is that the seeing and the touching were never supposed to be the same thing, and that a species which can look 94% of its universe in the eye, knowing it will never arrive, and still build ships anyway, is a species worth being. Thank you for traveling with me tonight. All the way from a steel table on a launch pad to the last bound shore of the reachable universe. If this journey meant something to you, take a second to like this video and subscribe. It genuinely helps this channel keep asking questions this size. And the next time you are out under a dark sky, find the faint smudge of Andromeda, the most distant thing your eyes will ever hold. And remember, by the right clock, it is 28 years away. Good night.